I welcome you all in the seventh lecture on psychrometric processes. Now we are going to discuss about two very important psychrometric processes known as sensible heating and sensible cooling process. When a given sample of moist air is made to flow over a bank or battery of heating or cooling coil, the thermodynamic state of air changes. During this process of heating, its dry bulb temperature increases, and during the process of cooling, its dry bulb temperature decreases. But the important feature of this sensible heat process is that during this process of sensible heating or sensible cooling, the specific humidity of the moist air does not change, means its water vapor content is not at all changing during this process. So that is what exactly we mean by a sensible heat process, means the amount of heat added to a working substance without causing any its phase change. So the working substance simply undergoes either a rise in temperature or a fall in temperature when the heat is added to or removed from the working substance. So during this sensible heating process, we notice from this psychrometric chart that if the initial state of the moist air is at point number A having a dry bulb temperature TA and a corresponding value of the specific humidity is omega A. If this psychrometric state of this moist air is altered in such a way that it moves along this horizontal line and acquires a new position at point number B where its dry bulb temperature has gone up from TA to TB, but the moisture content or the specific humidity level does not change. So under this scenario, the air is said to be simply sensibly heated up. So we can notice that during this process of sensible heating, air can be heated up to any desired value of the temperature. There is no limit on that. But when the initial state of the moist air is at point number B and it is brought in contact with some cooling coil, so ultimately the temperature of the air would change. So the temperature of the air would change along the path B to A. So the final temperature of the air becomes TA. So under this scenario, when there is no change in the specific humidity, only a change in the dry bulb temperature is there. Either the dry bulb temperature increases or decreases. So accordingly, the air is said to be sensibly heated up or cooled down. So there is one limit during the sensible cooling process that if we maintain the cooling coil at lower and lower temperature, so air is going to be sensibly cooled down, but air can only be cooled down up to its dew point temperature. If we try to maintain the cooling coil at a temperature which is lesser than the dew point temperature, so ultimately it will result into the removal of the moisture. So condensation of the moisture will take place, and that will ultimately bring down its moisture content or the specific humidity. So as far as the sensible heating is concerned, this given sample of the moist air can be heated up to any desired value of the temperature, whereas during the sensible cooling is permissible only up to the dew point temperature of the given sample of the moist air. So let us continue our discussion on the sensible heat process, and we shall now try to determine as to how much amount of heat is either required to be added up or to be taken away from the air, so that the given sample of the moist air undergoes either a sensible heating process or sensible cooling process. So the amount of sensible heat which is added to the air when it undergoes a rise in temperature from TA to TB here. So its thermodynamic state on the psychrometric chart changes from the point number A to point number B. So this is going to be a case of sensible heating of air. So the keeping its specific humidity or the moisture content constant, the dry bulb temperature of the air is going to be increased. So the amount of heat in the form of sensible heat added to the air would be equal to mass flow rate of the air, that is MA stands for the dry air part, and this is multiplied by HB minus HA, that is the enthalpy at point number B and enthalpy at point number A. Now it can further be expressed as this enthalpy change can further be expressed in terms of Cp and the change in temperature. So it's going to be Ma into Cp multiplied by TB minus TA. So definitely here the term Cp, I think all of you guys still remember that Cp is nothing but the humid specific heat, which is given by Cpa plus omega times Cpv. So it contains both the specific heat at constant pressure for the dry air part and the specific heat at constant pressure for the water vapor content, and of course it is going to be multiplied with omega, that is the specific humidity of the given sample of moist air. So this is going to be my equation number 1. So when we separate it into the two components, Cp is Cpa plus omega times Cpv. So this equation number 1 can be written down as Ma into Cpa multiplied by Tb minus Ta plus Ma into omega into Cpv multiplied by Tb minus Ta. So when we insert the values of Cpa and Cpv in this equation, what we get is the amount of heat added to the air in the form of sensible heating. So that is going to be equal to Ma 1.005 plus 1.88 omega into Tb minus Ta. So we have already made it clear that the Cp is the humid specific heat here. So this heat denoted by the subscript S, that is Qs, is called the sensible heat. So definitely if a building is there which is required to be air conditioned and that particular building receives or loses the heat due to the transmission or other reasons, it is supposed to have sensible heat load. So heat gain in building will require the conditioning of air to lower temperatures, causing a cooling load on the air conditioning equipment, and however the heat loss in the building will require the heating of air, which ultimately results into a heating load on the refrigeration and air conditioning equipment. So it was a case of sensible heating of air when the sensible cooling is required. So ultimately the thermodynamic state of air would interchange. Point number B becomes now point number A, that is the initial state of the given sample of moist air, and point number A takes the is replaced by point number B. So everything remains unchanged, only the direction of the process changes. Earlier in the case of sensible heating, we were moving from point number A towards point number B. In case of the sensible cooling of the same sample of moist air, we would be moving along the path B towards point number A. So simply by interchanging the points, we will come to know how much amount of heat is required to be taken out of air so that it can undergo a sensible cooling process, so that its dry bulb temperature can be reduced from certain initial value to a final value, which is obviously greater than its dew point temperature, keeping its specific humidity or the moisture content constant. Now we can have a look on various thermodynamic properties, how they change when a given sample of the moist air is either sensibly heated up or sensibly cooled down. So obviously when the given sample of the moist air is sensibly heated up, its thermodynamic state would change from point number A and up to point number B. So obviously the dry bulb temperature is going to be increased during the case of sensible heating, and when we are thinking of sensible cooling, obviously its dry bulb temperature is going to be decreased. During the case of this sensible heating, there is no change in the specific humidity or the moisture content, but the specific enthalpy of this particular moist air is going to be increased. At point number A, we are closely at 40 kilojoules per kg of dry air, and at point number B, the corresponding value of the enthalpy is 55 units. So obviously during this case of sensible heating, the enthalpy would increase, and during the case of sensible cooling, there will be a decrease in the enthalpy of the moist air. When we look at the specific volume, that is the humid volume, obviously the specific volume is going to be increased. These dotted blue lines, they are basically representing the specific volume. So passing through the point number A, there is a definite value of the specific volume, and specific volume increases in this direction. So obviously at point number B, the specific volume is going to be increased. Obviously the air is getting heated up, so there will be an increase in the specific volume. So during the case of this sensible heating, there will be an increase in the specific volume, while in case of sensible cooling, there will be a that is a decrease in the specific volume. Wet bulb temperature is obviously going to be increased during the case of sensible heating, and during sensible cooling process there will be a decrease in the wet bulb temperature. Percentage saturation, obviously it decreases when the air is sensibly heated up, because the relative humidity is also going to be decreased. When we look at the relative humidity value at close to point number A, it's around 60%, whereas at point number B it is somewhere between 20 to 30%. So obviously the percentage saturation is going to be decreased, means more amount of water vapor would be needed for saturating the moisture which is now present at point number B. Whereas during this sensible cooling process, the percentage saturation increases. Moisture content, obviously, while moving along this horizontal path, sensible cooling or sensible heating, there is no change in the specific humidity or the moisture content. Dew point temperature, obviously the dew point temperature does not change at all. However, the dew point temperature is only considerable when we are thinking of sensibly cooling down the air. During the sensible heating of air, there is no point considering the dew point temperature, because air can be heated up to any desired value of the temperature. Only in case of the sensible cooling, when we are moving from the point number B and passing through point number A, and eventually we will end up only up to dew point temperature. Beyond this we cannot think of cooling the air sensibly. Means if the cooling is carried out beyond this dew point temperature, there will be a decrease in the specific humidity, or the moisture will drain out because of the condensation. Vapor pressure, because there is no change in the moisture content or the specific humidity level. Vapor pressure, that is partial pressure of the water vapor, it does not change either. It is a case of sensible cooling or sensible heating process. Right here you can have a look of two sensible heaters. This is a quite common device which is mostly available in most of the houses, and it is universally used during the winter season. So obviously there is a filament, there is a heating element there, so it basically takes in the air from here. There is a flow augmentation device, that is a fan is there. This particular fan sucks in the air from the room, and this particular air, while it flows over these heating coils, it gets heated up, and this heated air is ultimately supplied into the room. So ultimately air is getting recirculated over and over again over this heating coil. So this is going to be a case of sensible heating. So but the important aspect of sensible heating is that during this process of sensible heating, what happens, the percentage saturation decreases, and also it results into a decrease in the relative humidity. So when the heater is kept inside the room, so it basically makes the air more drier and drier, so it takes away the moisture, much greater amount of the moisture from our skin and everything. We have seen in the previous slide that the amount of sensible heat added to or removed from the air is given by expression Qs equal to Ma into Cp into delta T. So in this particular equation, Ma denotes the mass flow rate of the dry air. Usually the flow rate of air is expressed either in cubic feet per minute, which is denoted as CFM, or in cubic meters of air per minute, which is denoted as CMM, rather than mentioning it in kg per second or kg per hour in air conditioning work, because most instruments read either CFM or CMM. Of course, the same quantity by weight of air is leaving the unit as is entering, but the CFM or CMM is greater. This variation in volume can lead to misunderstanding and error, such as selection of the wrong size equipment unless clearly specified. Problems can be avoided by always indicating the temperature and pressure at which the CFM or the CMM is specified. However, when rating the capacity of equipment such as fans, coils, and air handling units, manufacturers do not know the condition of temperature and pressure that each user will apply. In order to avoid misunderstandings, the CFM or CMM of the equipment is often expressed at standard air conditions. So now the mass flow rate of dry air can be calculated from equation number 2. So mass flow rate of the dry air is expressed as the volumetric flow rate multiplied by the density. So where here the QV is the volumetric flow rate of air, and now we can express this volumetric flow rate in cmm. Cmm stands for cubic meter per minute. So we have this particular equation 2 modified in this particular fashion. So ma dot is going to be expressed as cmm divided by 60 multiplied by rho. So units are going to be kg of dry air per second. So let it be my equation number A. Now for the purpose of calculations, the standard air is taken at 20 degrees Celsius dry bulb temperature and 50% relative humidity. The density of standard air is approximated to 1.2 kg per meter cube of dry air. The value of humid specific heat is taken as 1.0216 kilojoules per kg of dry air per Kelvin. So substituting these values in the expression for sensible heat, Qs equal to Ma into Cp into Tb minus Ta. So what we are going to do is we are going to insert the value of Ma from the equation number A into equation number 1, and also inserting the value of Cp here. So that is going to give us a value cmm into rho, density is 1.2 divided by 60, and Cp, that is specific heat is taken as humid specific heat is taken as 1.0216. So it is going to be cmm into 1.2 multiplied by 1.0216 divided by 60, and of course this Tb minus Ta or Ta minus Tb, it is nothing but delta T. So when we look at the unit of this entire expression, it is simplified to 0.0204 cmm into delta T, and unit is very important, it is in now kilowatt. So this is very important equation, because with the help of this equation, simply by knowing the volumetric flow rate cmm and what amount of temperature change is required, we can come to know that how much amount of heat is either required to be supplied to the air or is to be taken away from the air, so that it undergoes either a sensible heating process or sensible cooling process. It may be noted that whereas simple heating of the moist air can be done to any desired temperature that we have already discussed, simple cooling can be done only up to the dew point temperature, that is up to Td. So cooling below this temperature definitely will result in the condensation of the moisture. Here you can see some real pictures of heating or cooling coils which are used in air conditioning equipments. So you can see here a copper pipe which is having multiple folds here. So each pipe is separated from the second one, and they are also having fins mounted over them, so that the flow of air over these tubes is uniform. Here also in this particular picture, these are the fins which are placed between these series of the tubes. These are the tubes which carry the either the refrigerant or some hot fluid. If it is required, air is required to be sensibly heated up, so ultimately the hot water will ultimately flow through this, and if it is going to be sensibly cooled, definitely it will carry the chilled water through them. So the tubes may have the single pass, or it may have the multiple pass also. So there may be a multiple rows of the cooling or heating coils. Now we are going to talk about a very important and very vital parameter, which is known as the bypass factor. Bypass factor is a very important parameter because it throws light as to how much efficient my heating or cooling coil is. So the efficiency or the effectiveness of the heating or cooling coil is ultimately reflected or is governed by the value of its bypass factor. Let us consider a case of sensible heating of air. There is a pipeline which is shown here by this purple color. So it carries the steam through it. So steam enters into this pipeline and it exits from here. The given sample of the unsaturated moist air, it is initially available at dry bulb temperature T1. It is made to flow over the bunch of these tubes. We have seen in the previous slide, while looking at the actual pictures of the heating or cooling coil, we observed that the tubes are having a finite distance. Means each tube is separated from the another one by a definite amount, and they are also having the fins in between them. So ultimately, when this air, unsaturated moist air, flows over the tubes which is carrying the steam at high temperature, so the air gets heated up because the walls of the tubes are impervious. So ultimately there is no mixing of the air molecules with either the steam or the hot wire which is flowing through the tube. So the moisture content of the air does not change, it remains as it is, only its dry bulb temperature changes. We assume here that the heating coil is maintained at a temperature of T3. When we look at the temperature of this air coming out of this system, it is at T2. Obviously, this temperature of air at the exit is going to be greater than its initial temperature, but this T2 is observed to be lesser than the temperature of the heating coil. So temperature of air coming out of the apparatus T2 will be less than T3 in case the coil is a heating coil, and more than T3 in case the coil is a cooling coil. So in this particular figure, let 1 kg of air at temperature T1 is passed over the coil having its temperature as T3. So when air passes over a coil, some of its say x kg just bypasses unaffected, while the remaining 1 minus x kg comes in direct contact with the coil. So this bypass process of air is measured in terms of a bypass factor. The amount of air that bypasses or the bypass factor depends on the following factors: the number of fins provided in a unit length, that is the pitch of the cooling coil fins, the number of rows in a coil in the direction of flow, and the velocity of flow of air. So while we look at the figure number 2, we assume here that the 1 kg of air initially at temperature T1, it is made to flow over the heating or cooling coil. This coil is maintained at a temperature of T3. So we assume that out of this 1 kg of air, x kg of air, it does not come in contact with the heating or cooling coil surface, because there is a finite separation between each tube, and they are also having the fins mounted between them. So there are certain molecules of air which do not physically come in contact with the outer surface of the heating or cooling coil. So we assume here that x kg out of 1 kg is getting bypassed. It does not come in contact with the surface of the heating or cooling coil. Only 1 minus x kg of the air physically comes in contact with the surface of the heating or cooling coil, and its temperature, the temperature of 1 minus x kg of air, is actually changed from T1 to T3. Now again at the exit of here, we have got 1 minus x kg that is totally affected by the heating or cooling process. So its temperature has changed from T1 to T3, and x kg of air, it does not come in contact with the heating or cooling coil surface, and it remains at its initial temperature of T1. So ultimately here at the exit section, we are having a mixing of two air streams. One is at T1 temperature, another is at T3 temperature, and their quantities are different. This is x kg of air which is getting bypassed, and 1 minus x kg of air which is actually coming in contact with the surface of the heating or cooling coil and getting its temperature changed from T1 to T3. So at the exit, again we have the mixing of this 1 minus x kg of affected air with x kg of unaffected air, and finally we get 1 kg of air at temperature T2. So it's obvious that if the length of this cooling coil is going to be greater and greater, there is more contact time available for the air. So ultimately there is more possibility that its temperature would approach T3, that is the temperature of the heating or cooling coil. Ultimately, if the spacing between the tube is also increased, so ultimately there is more likelihood that more number of air molecules will remain unaffected. Obviously, when we increase the flow velocity, so retention time of the air molecules over this cooling coil or heating coil surface is also getting reduced. So in that case, it is quite sure that the temperature at the exit is definitely going to be different from the temperature of the heating or cooling coil surface. So here we have got three vital parameters which are going to affect the amount of bypass, that is the number of fins provided in a unit length, that is the pitch of the cooling coil fins, the number of rows in a coil in the direction of flow, and the velocity of flow of air. So it may be noted that bypass factor of a cooling coil decreases with decrease in fin spacing and increase in the number of rows. So now what we can do is we can make energy balance at the exit of this particular section. Here we are having the mixing of the two air streams, x kg of air at temperature T1 and 1 minus x kg of air at temperature T3. And finally the air leaving the system is going to be again 1 kg, and it is now available at temperature T2. So making the energy balance at this particular junction, we get x into Cp into T1 plus 1 minus x into Cp into T3 is going to be equal to 1 into Cp into T2. So this is obviously x into Cp into T1. This is for first air stream, its enthalpy. For second air stream, which is flowing over the heating or cooling coil and getting its temperature changed from T1 to T3, it is 1 minus x kg is basically the quantity or mass flow rate multiplied by Cp into T3, and finally at the outlet of this we have got 1 kg Cp into T2. So from here we determine the value of x as T3 minus T2 divided by T3 minus T1, that is temperature of the heating or cooling coil minus the temperature of air at the exit divided by the temperature of heating or cooling coil minus the temperature at the inlet. So here the term x is called the bypass factor of the cooling factor of the coil and is generally written as BPF. So for the case of heating, it is going to be T3 minus T2 divided by T3 minus T1. So it's quite clear by looking at the cyclomatic chart plotted for the sensible heating case and for the sensible cooling case. In the case of sensible heating, the heating coil is maintained at the highest temperature. Air is made to flow over this heating coil initially at temperature T1. So it flows over the heating coil, but all of the air is the temperature of the whole chunk of the air is not changed up to T3. Rather, it exits from the system at temperature T2. So for this case of the heating, it's going to be defined as T3 minus T2, that is the difference of temperature at the exit divided by the difference of temperature at the inlet. So it's T3 minus T2 divided by T3 minus T1. Whereas for the case of the cooling, it's slightly different. Now the air is made to flow over the cooling coil at temperature T1. Cooling coil is maintained at temperature T3, whereas the actual exit of the air from the system is now at T2. So for the cooling process, it is going to be that the subscripts are going to be interchanged. Now it is T2 minus T3 divided by T1 minus T3. So we observe that in the case of sensible heating, the temperature of air which is exiting from the system is lesser than the temperature of the heating coil, whereas in case of the sensible cooling, the temperature of the air which is exiting the system is greater than the temperature of the cooling coil. The bypass factor for heating or cooling coil may also be obtained as discussed below. Let the air passes over a heating coil which is maintained at a temperature of T3. So here we can assume that through the tubings of the heating coil the steam is being supplied. So the temperature of this heating coil remains constant and only the condensation of the steam would be there. So the outer surface of this the heating coil, it remains at constant temperature. The moist air, that is unsaturated air, approaches this heating coil at lower value of the dry bulb temperature, and as it flows over the bank of tubes of the heating coil, its temperature increases. The air gets heated up during its course of flow over the bunch of heating tubes. The temperature distribution of air passing through the heating coil is as shown in the figure number 1. So therefore the sensible heat given out by the coil is given as Qs is equal to UACTm. This is equation number 1. Here the terms are quite important. U is the overall heat transfer coefficient, AC is the surface area of the coil, and Tm is logarithmic mean temperature difference. We know that for this sort of heat transfer, where one fluid simply undergoes a phase change and there is no direct mixing of the two fluid streams. Steam flows through the pipeline and over these tubes the air is made to flow. So for this type of heat exchanger, the logarithmic mean temperature difference is given as T2 minus T1 divided by log of T3 minus T1 divided by T3 minus T2. So how do we determine this LMTD or log mean temperature difference? It is nothing but the temperature difference at the inlet of the heat exchanger minus temperature difference at the exit of the heat exchanger. So in this numerator part we have got T3 minus T1 minus T3 minus T2. So finally we are left with T2 minus T1 in the numerator divided by log of the temperature difference at the inlet divided by temperature difference at the exit. Now we know that for this case of sensible heating, the bypass factor is defined as T3 minus T2 divided by T3 minus T1. So in this expression for log mean temperature difference, this Tm can be expressed as T2 minus T1 divided by log of 1 over bypass factor, because this bracketed quantity is nothing but the inverse of the bypass factor or the reciprocal of the bypass factor. Now equation 1 gets modified to U AC T2 minus T1 divided by log of 1 upon BPF. So we know that the heat added during the sensible heating is equal to mCp delta T. So Qs is going to be mass flow rate of the air multiplied by its humidity specific heat and multiplied by that is the temperature rise it undergoes during the heating process. Here the Cp is the humidity specific heat. Its value is 1.022 kilojoules per kg Kelvin, and Ma is nothing but the mass of the air passing over the coil. So now we can equate the equation number 2 with equation number 3. So upon equating the equation number 2 with equation number 3, what we get is log E 1 upon BPF is equal to UAC upon MA into CP. So here we get bypass factor expressed in terms of this U overall heat transfer coefficient, AC, that is area of the heating coil, MA is the mass flow rate of air, and CP is the humidity specific heat. So finally we get an expression for bypass factor equal to e raised to minus UAC upon, substituting the value of Cp here, 1.022 into Ma. This is the equation number 4. So proceeding in the same way, we can derive the equation 4 for a cooling coil also. Now we look at the efficiency of heating or cooling coil. Obviously, it's clear from the preceding discussion that greater the value of bypass factor, more and more amount of air will not come in contact with the heating or cooling coil surface. So the performance of a heating or cooling coil is measured in terms of a bypass factor. A coil with low value of the bypass factor has got a better performance. So efficiency of the heating coil is nothing but 1 minus bypass factor. So expressing it in terms of these temperature ratios, it comes out to be T2 minus T1 divided by T3 minus T1 for the case of sensible heating, and for the case of sensible cooling, the efficiency of the cooling coil is going to be equal to T1 minus T2 divided by T1 minus T3. Now we take up another very important psychrometric process, which is known as the latent heating and cooling process, and also sometimes called as the pure humidification or dehumidification process. As we understand that the process of adding water vapor to the air is nothing but the humidification, and the removal of water vapor from the air is termed as dehumidification. When the state of air is altered along the constant dry-bulb temperature line, as shown in figure 1, initial state of the moist air is at point number B, and its thermodynamic state is changed along this vertical line, and the final state of the moist air is at point number C. So what we notice is that the temperature at point number B and temperature at point number C are same. So there is no change in the dry bulb temperature of the air, whereas its specific humidity level goes up. Initially at point number B, the specific humidity is omega B, which has now increased to a value omega C at final state of the moist air. So ultimately, the moisture in the form of vapor has to be transferred to change the humidity ratio of the air, and this transfer of the moisture is given by G, which is equal to, that is the mass of water vapor at point number C minus mass of water vapor initially the air had at point number B. So it is going to be expressed as Ma times omega C minus omega B. So because Ma into omega C is nothing but the mass of water vapor at point number C, and Ma into omega B is nothing but the mass of water vapor at state number B. Let us call it as equation number 1. Because of this change in the humidity ratio, there is also a change in the specific enthalpy of the air. When we look at the enthalpy scale corresponding to point number B, the enthalpy value is Hb, which has now increased because of the addition of the moisture to a value Hc. So because of this change in the humidity ratio, there is also a change in the specific enthalpy of the air given by Hc minus Hb. In air conditioning practice, this change in enthalpy due to the change in the humidity ratio is considered to cause a latent heat transfer. Obviously, in humidification, the enthalpy of the air increases due to the enthalpy of the water vapor added. That is why this process is called a latent heat change. So now we can express this, the latent heat transfer QL is equal to Ma into Hc minus Hb. It is going to be expressed because Ma into Hc is nothing but Cp into Tc plus Hfg naught into omega C. Likewise, we can also express Hb in terms of this Cp and omega. So it's going to be Cp into Tb plus Hfg naught into omega B. You must remember that the humid specific heat is given by the expression Cpa plus omega times Cpb. So what we get here is this, since temperature at point number C and temperature at point number B are same, so these two terms cancel out. So finally what we are left with is Ma into Hfg naught multiplied by change in specific humidity, that is omega C minus omega B. We are aware that we defined this Ma into omega C minus omega B. This is nothing but the change in the moisture level of the air as it undergoes a humidification process. So this is denoted by G. So Ma and this bracketed quantity omega C minus omega B, it is expressed as G, and latent heat of evaporation at 0 degrees Celsius is, its value is known to us, and it is nothing but 2500 kilojoules per kg. It is important to mention here that the pure humidification and dehumidification without a sensible heat change do not occur often in practical air conditioning processes. However, the concept is important to understand in analyzing the conditions. In the above derivation, Cp has been taken as the same for both B and C thermodynamic states. It is evident that though the term latent heat appears to be a misnomer, the quantity QL is proportional to the latent heat of vaporization Hfg naught. It implies that if water is to be evaporated or condensed at the temperature of air, the required heat transfer would be QL. Accordingly, if a building gains or loses the moisture, it is supposed to have a latent heat gain. A gain of moisture will require the condensation of the moisture for the dehumidification of air in the air conditioning apparatus, and hence it imposes a cooling load on the air conditioning apparatus. On the other hand, if there is a building which is continuously losing the moisture, it will basically require the evaporation of water for humidifying the space, and for that purpose the ultimately heating load is imposed on the air conditioning apparatus. So substituting 2500 for Hfg naught in equation number 2 and using the expression for mass flow rate of the dry air MA using this expression MA equal to CMM into rho divided by 60, that is kg of dry air per second, where CMM is nothing but the volumetric flow rate cubic meter per minute. So we express this latent heat transfer as QL equal to MA into HFG naught multiplied by omega C minus omega B. So MA can be expressed in terms of this CMM and density. Density is known to us, it is 1.2. MA is nothing but CMM by 60 into 1.2. HFG naught is 2500 or 2501. Omega C minus omega B is nothing but the change in specific humidity, so it is denoted by delta omega. So finally we get an expression for the amount of heat transferred in the form of latent heating or cooling, QL equal to 50 cmm delta omega, and the unit is quite important, it is expressed in kilowatt. Now there are certain points which should be clearly understood as far as the latent heating or cooling process is concerned. If water were simply evaporated in the air without providing the required heat, the air would cool down. This process will be described shortly in the coming lectures. Therefore, the heating equipment must provide the sufficient heat to prevent the cooling of the air. Another method of humidifying is to generate the steam in a separate source and inject it into the air to be humidified. Humidification is a desirable process in winter air conditioning. Natural air conditions in the winter have a very low humidity, a condition which is unacceptable for good comfort. Quality environmental control system should include the winter humidification. Dehumidification is the reverse of the humidification. All of the equations for the latent heat change hold true in this case. Heat must be removed from the air to dehumidify it, that is, to condense water vapor from it. Dehumidification is not a very commonly used process and the need arises only in specialized industrial air conditioning. It is usually combined with sensible cooling or heating.